From clean code to clear communication, welcome to English Not Null, where you learn to present your work with confidence and precision.
Welcome to English Not Null. I'm the guide, and today we're going to explore one of the most important technologies in distributed systems, Apache Kafka. What is Kafka? Why do 80% of Fortune 100 companies use it? And most importantly, how can you use this knowledge in your system design interviews? In today's video, we'll follow a conversation between Emma, a curious junior developer, and John, a senior engineer with years of experience. Together, they'll explore Kafka from the most basic concepts to advanced techniques. What's special about this video is that we'll learn through a real conversation. You'll not only learn about Kafka, but also improve your listening and speaking skills through technical discussions. Throughout the conversation, you'll learn what Kafka is and why it's important. Core concepts like producers, consumers, topics, and partitions. How to use Kafka in real-world systems. Strategies for scaling and handling failures, and best practices that big tech companies are applying. I encourage you to listen actively. Pay attention to how Emma asks questions and how John explains complex concepts using simple examples. This is exactly how you'll need to communicate in international work environments. Are you ready? Let's begin our journey exploring Kafka with Emma and John.
Hey John, I've been hearing about Kafka everywhere lately, especially in system design discussions. Can you help me understand what it actually is and why it's so important?
Oh, absolutely. Kafka is a really fascinating piece of technology. So, at a high level, Kafka is what we call an event streaming platform. Think of it like a superpowered message queue that can handle massive amounts of data.
Okay, so it's like a queue. But what makes it special? I mean, we have regular queues, right?
Great question. Let me give you a concrete example that might help. Imagine you're building a website that provides real-time updates for World Cup games. Every time there's a goal, a booking, or a substitution, you need to update your website.
Right, so events are happening and we need to process them somehow.
Exactly. So in Kafka terminology, we have what's called a producer. That's the server or process that puts events onto the queue. In our case, it could be someone with a laptop at each game sending updates.
And on the other side, we have something reading those events?
Yes, that's called a consumer. The consumer reads events from the queue and updates your website. Now here's where it gets interesting. What happens when FIFA suddenly decides to expand the World Cup from 48 teams to, let's say, 1,000 teams, and all games start at the same time?
Oh wow, that's a lot more events all at once. I'm guessing our single server would struggle?
Exactly. The server holding the queue would run out of space, and you know what the solution is, right? It's something we hear about all the time in system design.
Scale horizontally? Add more servers?
Perfect. But now we have a new problem. If we just randomly distribute events across multiple servers, we might end up with a mess. A goal could be processed before the match even started, or players could be booked for fouls they never committed.
Ah, I see the issue. The ordering gets messed up when we split things across multiple servers.
Exactly. And this is where Kafka introduces a key concept called partitioning. Instead of randomly distributing events, we can distribute them based on something meaningful, like the game they're associated with.
So all events from the Brazil versus Argentina game would go to one queue and all events from the France game would go to another queue?
Bingo. This way, we can guarantee that events from a single game are processed in order. We can't guarantee that the 81st minute goal from France happens after the 80th minute goal from Argentina. But that's okay because what we really care about is the order within each game.
That makes sense. So this partitioning concept is fundamental to how Kafka works?
Absolutely. In Kafka, these individual queues are called partitions, and they're just append-only log files. Think of them like a log file on disk where we keep adding messages to the end.
So we have partitions. But what happens when we have so many events that even our consumer can't keep up?
Great question. The logical solution is to add more consumers. But if we just add more consumers, Without any coordination, we might have multiple consumers reading the same event.
Right, so we'd end up with duplicate processing. That would be bad.
Exactly. So Kafka introduces something called consumer groups. When consumers are part of the same group, Kafka ensures that each event is only processed by one consumer in that group.
That's clever. So it's like having a team of workers where each task is only given to one person.
Perfect analogy. Now, let's say FIFA decides to expand to other sports, basketball, tennis, whatever. We don't want our soccer website showing basketball events, right?
Of course not. So we need some way to separate different types of events.
Exactly. And that's where Kafka's topics come in. Topics are just logical groupings of partitions. So consumers can subscribe to specific topics. Our soccer consumers only get soccer events. Basketball consumers only get basketball events.
Okay, so let me make sure I understand the hierarchy. We have topics which contain partitions, which contain the actual messages?
You've got it. And here's an important distinction that confuses people. Topics are logical groupings that exist in code, while partitions are physical. They're the actual log files on disk. Topics are for organizing your data. Partitions are for scaling your data.
That's a really helpful way to think about it. So when I'm using Kafka, I publish to a topic, but behind the scenes, it's actually going to a specific partition?
Exactly. And how it chooses which partition is really important. If your message has a key, we call it the partition key, Kafka will hash that key and use the result to determine which partition to use.
So messages with the same key always go to the same partition?
Yes. That's how we maintain ordering for related events. In our soccer example, we might use the game ID as the partition key, so all events from the same game stay together and in order.
What happens if I don't specify a key?
Then Kafka will just distribute messages randomly across partitions. This works fine if you don't care about ordering, but if you need related messages to be processed in sequence, you definitely want to use a key.
This is really cool. So when would I actually use Kafka in a real system? Are there specific scenarios where it shines?
Oh, there are tons of use cases. The first big category is anytime you need a message queue. For example, think about YouTube. When you upload a video, they need to transcode it into different resolutions, 480p, 720p, 1080p, and so on.
Right, and that transcoding probably takes a while.
Exactly. And the user doesn't need to wait for it. So they can put a message on Kafka saying, transcode video ID 123, along with the S3 location of the video. Then consumer services can pull these messages and do the transcoding asynchronously.
That makes sense. The processing can happen in the background while the user continues using the site.
Exactly. Another great use case is when you need in-order processing. Think about Ticketmaster when a really popular concert goes on sale. They might put users in a waiting queue and only let people through in groups to avoid overwhelming the system.
Oh, so they'd put user requests on Kafka and then periodically pull batches of them off the queue?
Precisely. And because Kafka maintains order within a partition, they can ensure fairness, first come, first served.
What about when you want to decouple producers and consumers so they can scale independently?
That's another perfect use case. Imagine a coding competition platform like LeetCode. You might have 100,000 users all submitting code at once during a contest.
So you'd want to scale up the servers handling submissions, but maybe not the servers actually running the code?
Exactly. The submission servers can scale horizontally to handle the burst. Put all the submissions on Kafka, and then you can have just a few workers pulling submissions off the queue and executing them. This way you can scale each part of your system independently based on its specific needs.
That's really smart. What about streaming use cases? I keep hearing about Kafka being used for real-time data processing.
Great question. Streaming is when you need to process a continuous flow of data in real time. A classic example is ad click tracking. Every time someone clicks an ad, you put that event on Kafka, and then you have stream processors like Flink consuming those events to give advertisers real-time statistics.
So it's like having a fire hose of data that you need to process as it comes in.
Perfect analogy. And another streaming pattern is pub/sub, where you want multiple consumers to process the same stream of events. Think about Facebook Live comments. When someone comments on a live video, That comment needs to be sent to all viewers watching that stream.
So you'd put the comment on Kafka as a topic, and all the servers connected to viewers would subscribe to that topic?
Exactly. Each server would see the comment and send it to their connected users, making it appear in real time across all viewers.
This is really powerful stuff. But what about when things go wrong? How does Kafka handle failures and ensure data isn't lost?
Great question. Kafka has really strong durability guarantees. Each partition has a leader replica that handles all reads and writes, plus multiple follower replicas that act as backups.
The leader goes down, one of the followers can take over.
Exactly. And there are configuration settings you can tune. The replication factor determines how many copies of each partition you keep. The default is 3. And the ACK setting determines how many replicas need to acknowledge a message before it's considered successfully written.
So there's a trade-off between durability and performance?
Exactly. If you set ACKs to all, every replica must acknowledge the message, which is maximum durability, but slower. If you set it to 1, only the leader needs to acknowledge, which is faster, but less durable.
What about when consumers fail? How does Kafka handle that?
Good question. Consumers periodically commit their offset, basically telling Kafka, I've successfully processed message number X. If a consumer crashes, it can restart and pick up from where it left off.
And if you have a consumer group and one consumer crashes,
Kafka will automatically rebalance the remaining consumers to cover the partitions that the crashed consumer was handling. It's pretty seamless from the application's perspective.
that's impressive. Now what about scaling? What happens when my Kafka cluster needs to handle more data than it can manage?
Well, first you should do the math. A single well-configured broker can typically handle about 10,000 messages per second and store about a terabyte of data. If your system stays within those bounds, you might not need to scale at all.
But if I do need to scale?
Then you add more brokers, and this is crucial, you need to choose your partition key carefully. A bad partition key can create hot partitions where all your data goes to one partition and overwhelms it.
Can you give me an example of a bad partition key?
Sure, let's say you're building an ad-click aggregator and you partition by ad ID. If Nike launches a popular LeBron James ad, suddenly one partition gets overwhelmed with clicks while others sit idle.
So how would you fix that?
A few options. First, you could remove the key entirely and distribute randomly. This works if you don't need ordering. Second, you could use a compound key, like add ID : random number 1 through 10, to spread hot ads across multiple partitions. Third, you could implement back pressure to slow down producers when partitions get overwhelmed.
The compound key approach is interesting. So you'd take that hot Nike ad and spread it across 10 partitions instead of 1?
Exactly, though you'd lose strict ordering across those 10 partitions. It's always a trade-off.
What about message sizes? Are there any constraints I should be aware of?
Great question. While there's no hard limit, it's highly recommended to keep messages under 1 megabyte for optimal performance. A common mistake I see is people putting entire files on Kafka.
What's the right way to handle large files then?
Instead of putting the file itself on Kafka, store the file somewhere like S3 and put just the S3 URL on Kafka. So your message might be video ID 123 and S3 URL. The consumer can then download the file from S3 when needed.
That makes sense. Keep Kafka for coordination and metadata, not for bulk data storage.
Exactly. Now, what about error handling? Kafka handles most reliability internally, but your application code might fail when getting messages into or out of Kafka.
So I need to handle retries on both the producer and consumer sides?
Right. On the producer side, it's straightforward. The Kafka client libraries have built-in retry logic. You can configure how many times to retry and how long to wait between retries.
What about consumer retries? That seems more complex.
You're right, it is. Kafka doesn't have built-in consumer retry support, so you have to implement it yourself. The common pattern is to use a retry topic.
How does that work?
Let's say you're building a web crawler. You pull a URL from the main topic, try to fetch it, but the website is down. Instead of losing that URL, you put it on a retry topic with a retry count. Another consumer can pull from the retry topic and try again.
And if it keeps failing?
After a certain number of retries, you put it on a dead letter queue, basically a topic where failed messages go to die. Engineers can look at these later to debug what went wrong.
That's a neat pattern. What about performance. If I'm processing real-time data, how can I make sure I'm getting maximum throughput?
Great question. There are several techniques. First, you can batch messages in the producer. Instead of sending one message at a time, you can accumulate messages and send them in batches.
And I'm guessing you can also compress messages?
Exactly. The producer can compress messages using algorithms like gzip before sending them. Smaller messages mean more throughput.
But the biggest impact is still the partition key choice, right?
Absolutely. Good partitioning ensures your load is evenly distributed across all brokers and partitions, maximizing parallelism. It's always the first thing you should optimize.
One last question. How long does Kafka keep messages around? I assume it doesn't store them forever.
Good question. This is controlled by the retention policy, which you can configure per topic. There are two settings. Retention.ms controls how long to keep messages. The default is 7 days. And retention.books controls the maximum size before old messages are deleted. The default is 1 gigabyte.
So whichever limit is hit first triggers the cleanup?
Exactly. And in some systems, you might need to store messages for much longer. Maybe months for audit purposes or event replay. You can configure longer retention, but just be aware of the storage costs.
This has been incredibly helpful, John. Kafka seems like such a powerful tool for building scalable distributed systems.
It really is. And the great thing is that nowadays, you don't even have to manage the infrastructure yourself. Cloud providers offer managed Kafka services like AWS MSK and Confluent Cloud that handle most of the operational complexity for you.
But it's still important to understand these underlying concepts, especially for system design interviews.
Absolutely. Understanding when to use Kafka, how to partition your data, and how to handle failures will really set you apart in interviews. Plus, it's knowledge you'll use all the time in real-world systems.
Thanks so much for walking through all of this with me. I feel like I have a much better understanding of Kafka now, from the basic concepts all the way to the advanced topics like scaling and error handling.
My pleasure. Kafka is one of those technologies that seems complex at first, but once you understand the core concepts, producers, consumers, topics, partitions, everything else builds on that foundation. And remember, it's used by 80% of Fortune 100 companies, so it's definitely worth understanding well.
I'll definitely be practicing with these concepts and thinking about how to apply them in different system design scenarios.
That's the perfect approach. Try to think of Kafka not just as a message queue, but as a fundamental building block for distributed systems. Whether you're building real-time analytics, event-driven architectures, or just need to decouple your services, Kafka is often the right tool for the job.
Perfect. I'm excited to start incorporating these concepts into my system design practice. Thanks again, John.
Anytime, Emma. Good luck with your interviews.
And that was a very detailed conversation about Kafka between Emma and John. I hope you now have a comprehensive understanding of one of the most important technologies in distributed systems. We've explored Kafka fundamentals like producers, consumers, topics, and partitions, why partitioning is important and how to choose partition keys, real-world use cases like message queues, streaming, and pub/sub, strategies for scaling and handling failures, as well as performance optimizations and error handling patterns. One thing I want to emphasize, Kafka is not just a simple message queue. It's a fundamental building block for building modern distributed systems. From Netflix to Uber, from LinkedIn to Spotify, they all use Kafka to process millions of events per second. For those preparing for system design interviews, remember that Kafka often appears in questions about real-time data processing, event-driven architectures, microservices communication, and handling high-throughput systems. Now, practice what we've just learned. Try to explain Kafka concepts in English with friends or colleagues. Draw diagrams and walk through different scenarios. Remember, the best way to learn is by doing. In the comments below, let me know which concept in today's video you found most interesting, if you can think of any other use cases for Kafka, and what technology you'd like to learn about next. Don't forget to subscribe to the channel so you don't miss our upcoming videos. We'll continue exploring other technologies like Redis, Elasticsearch, and many more exciting topics. And, especially, if you like this dialogue format, please like the video so I know. I'll create more conversations between Emma and John about different topics. Finally, remember, technology is just a tool. What's most important is the ability to communicate and collaborate effectively. By improving your English skills through technical content, you're building two important skills at the same time. Keep learning, keep practicing, and most importantly, keep coding. I'll see you in the next video. Until then, happy coding,